Hello students. In this lesson, we are going to study about photochemical reaction of transition metals complexes. In content, we will cover Introduction, Jablonski diagram, Kasha's rule, quantum yield, and Photo-substitution reaction. Introduction. The term photochemistry generally applies to chemical modifications induced by interaction of light, that is, electromagnetic radiation, with matter. Photochemical processes are those in which the excited species dissociates, isomerizes, rearranges, or react with another molecule. It is the branch of chemistry which concerned with the chemical effects of light. Generally, this term is used to describe a chemical reaction caused by absorption of ultraviolet wavelength from 100 to 400 nanometer, visible light 400 to 750 nanometer, or infrared radiation 750 to 2500 nanometer. To initiate a photochemical reaction, two requirements need to be met. Number 1, the photon must have enough energy to initiate the photochemical reaction in the molecule. Number 2, the compound must be colored in order to be able to react with visible or near-visible photon radiation. The consequence of the absorbing light of molecules is the development of transient excited states with chemical and physical properties that differ greatly from the original molecules. Jablonski diagram. The Jablonski diagram is widely used in fluorescence spectroscopy to illustrate the excited states of a molecule and the radiative, non-radiative transitions that occur between them. The Jablonski diagram is named after Polish physicist Alexander Jablonski, who is regarded as the father of fluorescence spectroscopy. The Jablonski diagram, that drawn below, is a partial energy diagram that represents the energy of photoluminescent molecule in its different energy states. The naming of the electronic states is based on the spin angular momentum configuration of each state. Singlet states are denoted by S, and triplet states denoted by T. S0 is the singlet ground state of the molecule. S1 is the first excited singlet state, and Sn is the nth excited singlet state. T1 is the first excited triplet state, and Tn is the nth excited triplet state. In this diagram, the lowest and darkest horizontal line represents the ground state electronic energy of the molecule, which is the singlet state. At room temperature, majority of the molecules in a solution are in this state. The upper lines represent the energy state of the three excited electronic states. The upper darkest line represents the ground vibrational state of the three excited electronic state. The energy of the triplet state is lower than the energy of the corresponding singlet state. The first transition in Jablonski diagrams is the absorbance of a photon of a particular energy by the molecule, and this is indicated by a straight arrow pointing up. Absorbance is the method by which an electron is excited from a lower energy level to a higher energy level. And this energy of the photon is transferred to the electron. It is the fastest transition, in the Jablonski diagram, occurring on a timescale of order 10 raised to power minus 15 second. That electron then transitions to a different eigenstate, corresponding to the amount of energy transferred. Internal conversion. Internal conversion is an intermolecular process of molecule that passes to a lower electronic state without the emission of radiation. It is a crossover of two states with the same multiplicity, that means singlet to singlet, or triplet to triplet states. Transition from higher excited singlet states, that is, S2, S3, to the lowest excited singlet state, S1, is called internal conversion, IC. This is allowed transition, with the electron staying in the same multiplicity. Now, from excited singlet state, the molecule returns to ground singlet state by releasing energy in the form of light or UV radiation. This process is called fluorescence, which occurs on a timescale of 10 raised to power minus 10 to 10 raised to power minus 7 second, and it is shown by the green arrows in figure. Intersystem crossing. Intersystem crossing is a process where there is a crossover between electronic states of different multiplicity, that means singlet state to a triplet state. Some energy may be lost during transfer from S1 to T1 in the form of heat. It is known as intersystem crossing, ISC. This is forbidden transition between states of different multiplicity. After ISC, the molecule may lose energy in the form of light in going from the excited triplet state to the ground singlet state, T1, by emitting light state. This process is called phosphorescence. A consequence of being a forbidden transition is that the phosphorescence rate constant is very low, and phosphorescence therefore occurs on a much longer time scale than fluorescence, with typical phosphorescence lifetimes being in the range 10 raised to power minus 6 to 10 second. Now we will compare and see the difference between fluorescence and phosphorescence. In case of fluorescence, if a system absorbs radiant energy and then emits it almost instantaneously, within 10 raised to power minus 8 second, in the form of radiation, this process is known as fluorescence. Its emission ceases as soon as the source of exciting radiation is removed. It can be simulated in liquid, gases, and solids. It caused by transition from S1 to S0, which is a quantum mechanically allowed transition. Then come to phosphorescence. Here, if a system absorbs radiant energy and then emits after a long time in the form of radiation, then this process is known as phosphorescence. It continues for some time, even after the removal of source of exciting radiation. It mainly exhibited by solids. It caused by transition from T1 to S0, which is a quantum mechanically forbidden transition. Absorption and emission rates. Fluorescence emission occurs at a slower rate. Since the triplet to singlet, or reverse, is a forbidden transition, so the rate of triplet to singlet is typically slower. Therefore, phosphorescence emission requires more time than fluorescence. It is important to note that a Jablonski diagram shows what sorts of transitions that can possibly happen in a particular molecule. Each of these possibilities is dependent on the time scales of each transition. The faster the transition, the more likely it is to happen, as determined by selection rules. Therefore, understanding the time scales each process can happen is imperative to understanding if the process may happen. The table below compares the absorption and emission rates of some basic photochemical processes. Kasha's rule. The rule is relevant in understanding the emission spectrum of an excited molecule. Kasha's rule is a principle in the photochemistry of electronically excited molecules. The rule states that photon emission occurs in appreciable yield only from the lowest excited state of a given multiplicity. It is named for American spectroscopist Michael Kasha, who proposed it in 1950. The term multiplicity refers to the spin angular momentum of the level singlet states have a multiplicity of 1, and triplet states have a multiplicity of 3. Fluorescence will always originate from the vibrational ground state of the lowest excited singlet level, S1, while phosphorescence will originate from the vibrational ground state of the lowest excited triplet level, T1. Kasha's rule is a consequence of the fact that, in complex molecules, the rate constant of internal conversion and vibrational relaxation from the higher lying electronic levels is significantly greater than the emission rate constant back to the ground state from those levels. The rate of internal conversion between two electronic levels is inversely proportional to the energy splitting between those levels. The S0 and the S1 have the largest energy splitting, and the rate constant of internal conversion is comparable to that of fluorescence, and the S1 to S0 fluorescence emission is therefore observed. The higher lying electronic excited states are closer in energy, and therefore undergo faster internal conversion that outcompetes the fluorescence. Quantum yield. Since many photochemical reactions are complex and may compete with unproductive energy loss, the quantum yield is usually specified for a particular event. Quantum yield is a characteristic property of a fluorescent species. The efficiency with which a given photochemical process occurs is given by its quantum yield, phi. Quantum yield may define as the ratio of number of photons emitted through fluorescence to the number of absorbed photons. It ultimately relates to the efficiency of the pathways leading to emission of fluorescence, providing the probability of the excited state being deactivated by fluorescence, rather than by other competing relaxation processes. The magnitude of phi is directly related to the intensity of the observed fluorescence. The value of quantum yield vary from very low of 0.04 to very high value of the order 106. The higher the quantum yield values, the brighter the fluorophore, and stronger the fluorescence signal intensity. In order to determine the value of quantum yield of photochemical reaction, it is essential to know the number of moles reacting, and number of Einstein absorbed. Photo-substitution reaction. Photo-substitution reactions will be activated by irradiating the complex at a ligand field transition wavelength. These are promoted by light absorption at ligand field or DD transition frequencies, which is consistent with the bonding in complexes. If we wish to promote photosubstitution, it is usually necessary to avoid irradiating He complex at the frequency of its CT bands. For photosubstitution reaction, the observed chemical reaction in a given system will be the sum of the photoreaction and any dark reactions, thermally initiated reactions. Chromium 3 is a particularly favorable system for the study of photosubstitution, because the other oxidation states, like Cr2+ and Cr4+, are so much less stable than Cr3+. In photoaquation of symmetrical Crl6 complexes, as you can see here, for a given ligand, the quantum yield, usually 0.1 to 0.4, is independent of which band is irradiated. This suggests that the photoreaction occurs from the lowest excited state, a rule analogous to Kasha's rule for radiation emission. The quantum yield tends to rise with dq for the ligand L. For less symmetrical complexes, such as CRX5Y or CRX4Y2, the complex can displace either ligand, as shown in the reaction, where X is equals to NH3, and Y is equals to halide, or pseudo-halide, but NH3 is preferentially released by a factor of 20 to 50 in relative quantum yields. This is the opposite of the thermal reaction, which displaces only the Y- ion, where it is possible to define cis and tram isomers for the products of chromium 3. In photosubstitution reactions, the products always seem to have the cis configuration, even though isotope labeling studies have shown that there is a clear translabelization effect. This antithermal behavior suggests that the excited states of chromium 3 complexes are relatively stereomobile, in contrast to the ground states, which are stereorigid in thermal reactions. Metal carbonyls tend to lose a carbon monoxide on irradiation and to undergo immediate substitution. This tendency is so pronounced that the compound decomposes in daylight to form Ru3CO12, which presumably represents trimerization of RuCO4 intermediate. If the carbonyl is unsymmetrical, then substitution can involve either carbon monoxide or L. Usually, CO loss is favored, as shown below. In general, photosubstitution reactions of carbonyls seem to proceed by a dissociative mechanism. Because, in solution, the separated ligand is initially held in place by a solvent molecule cage. There are even a few cases in which a metal-alkyl bond is activated. Thank you.